So a feature of D2L that I want everybody to be aware of, I'm not really suggesting this as an alternative to using a flash drive, but flash drives can get lost. So anyways, if you go to Tools, Locker, you can upload files, any files you want within a limited amount of space. I've used up 9.5 megabytes of my total available 9.7. I need to figure out what it used. But anyways, you could upload any notes that you've taken there, you know, and then you'd have them available during an exam. Or if your machine gets wiped out, because you never know when a hard drive's going to crash or something's going to go wrong and they're going to reformat your machine. Happens all the time. If that happened and you lost all your work that you've been saving and that would upset you, I'd recommend uploading your files somewhere. I think everybody knows how to make a zip. You just go into the folder that you want to zip up, highlight everything, right? And then right click and do send to compressed folder. Or you could upload them all individually just as easily. So I had a question, are we doing anything with MindTap yet? Yeah, the first test has been due, you know, for like 3 weeks, but I keep pushing the due date back just so that people can keep playing with it, since you can take it multiple times. Unit 2 test also has a due date, I think for the 12th, which may be the date of our exam that I just posted. Yeah, so you'll want to get the March 2 exam. What is it? Now, I don't really need to do the review right now. It's going to cover chapters 1. It's going to cover chapter 2. It's going to cover, you know, our in-class assignments. And if I specify anything else on the review, we'll cover that as well. Really, anything that I've mentioned is fair game, but I really try not to just mention something first, you know, like on the first week, and then never mention it again, and then spring it to you on an exam. I don't think that's too cool. Alrighty, so the most common configuration for mainline logic. Let's throw a lot of techie terms. Generally, what this means is that your program is going to have a main section. And we kind of did that in the last time we did functions. And what is it going to do? It's going to set some stuff up. Then it's going to do some looping, and then it's going to do something with the results of that looping, or whatever it has to do at the end of the application. So for example, setting things up might involve, you know, attaching to a database, and then the looping would be reading from the database and, you know, printing out a table of people's paychecks or something like that, and then you close the database. Or you know, it's a video game. So the setup task is sitting there waiting, you know, for the person to put the coin in. When they put the coin in, it draws the map and it goes into a loop. You know, starts playing Pac-Man, looping over and over and over, redrawing all the things as they go around. And then once the game is over, it goes into the end stage thing, the end of the job thing. That's all kind of incorporated into a great big loop, of course. Looping is what computers are all about. No. Your declarations, your housekeeping. You have to open any files or set anything up. We're not doing stuff like that yet. Then go into a loop for whatever purpose. Whether you're just asking the user if they wish to repeat, you know, or enter a series of numbers, or you're reading through a file, or you're taking sensor readings, whatever. When it finally is done, whenever this condition is no longer true, you're at the end of the job. So while we are at it, you don't have to draw these things because I'm going to post them, but I'm going to use a lucid chart to do one more little talk about flowcharting. Which symbol do we use to start and to stop our flowcharts?
Terminator.
Yeah, the terminator. I'll be back. Okay. So, you can do a start or a stop. Or if you're doing a module, you can do, the module name, def module, and a return statement at the bottom. So like that, with some work between them. Then you have process blocks, which is stuff like maths. Well, let's do the declaration block. That's what you can do with one of the process blocks. You can do math calculations, that kind of things. Assignments, A is equal to 0, B is equal to B plus 1, Kilograms is equal to pounds times 2.2, whatever. You can have input and output. And of course, output corresponds right now to our print statements. But the output could also be writing out to a file. We'll do that later. Saving to a database, which we're not going to do. Unless we just really feel like doing something clever. Alrighty. Then we have this, the if. There are essentially two ways the if can go. You could have if condition, on that slide, their condition was not EOF. Right? Now, they didn't put the word if there. Well, that's because this is actually a while loop. The books never show using the word if for a while in your diamonds. I like them to be there. If you feel like leaving that word off, you can. So, if that condition, and then if it's true, you go off and you do something, whatever. If it's not true, you fall through. And then these are probably going to hook, well, not probably, they have to hook back together at some point. I like to use a little joiner. And then take that A out. Okay. So that is the equivalent in your Python code of doing this. If condition, colon, do something, right? Whatever that something is supposed to be. This could be a function call, it could be a whole series of statements. This is just kind of, then a miracle occurs, a fill in the blank. Okay. That is the way that one looks. If it's true, you do something. If it's false, you do nothing. But there's also the else version, which looks like this. If condition, do something, else, do something else. So let's make this do thing 1, and let's make this do thing 2. So to flowchart that, you have another box on the other side of the if. It'll look very similar, but, instead, it's going to look like this. You're going to have your condition there. It's going to come over here and do thing 1 if it's true. But if it's not true, come over here and do thing 2. Then they hook back up together. Little connector. Where's my connectors? Why are you not? Okay, fine. Usually I take the time to shrink the connectors to make them look less important. They don't need to be huge size. If you were doing this on an exam and time was of the essence, you wouldn't take the time to shrink it unless you just felt like it. Guess it didn't take that long. All right, so there we go. Two different versions of decisions. If it's true, do something, else do nothing. If it's true, do something. Now see, I used the word else. But there is no else in this first code, right? If you look at it, it was just this. It's easy to say else, but there's no else keyword there, right? There's just a positive condition or the absence of a statement. This is the one that has an else. I'm awfully tempted whenever I draw these things to go ahead and do the word else there, just so that it really reads like an if statement. You know, if this is true, go ahead and do some stuff, else do this. I like the way it looks, but it's not proper flow charting. The only reason I like doing that is because there's no else block. You never draw another one of these things and put else on it. Else is just for the compiler's benefit. There's no It's a keyword, but there's no block. It's not a process. It's just a direction on a flow chart. So I'm going to remove that because it's not technically correct. I wish that it was part of the standard or something like that. But just like the books never show putting the word ifs in your decision blocks, they don't show putting else there. Okay, so we got that, but there's decision block can also be used for looping. And the looping is what this slide showed. Dun, 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 like that. And those are while loops. And then we'll eventually hit another kind of loop called a for loop. So the same shape is used for that. Looks like this. I need something to anchor my stuff at the top too. Should be a start. I'll probably delete that shape. But anyways, we just needed something to go up to here. And then we would do this, while condition. And if that condition is true, you're going to jut off and you're going to do something. While x is greater than 0, subtract 1 from x. That kind of something. Then, once it's done with that, it's supposed to come back up to the top and hook up to the decision block again. The books show it going like this, drawing some line out to here and then hooking back up to the top. That's great. I guess I should start doing it that way since this textbook does it. I'll show you how I used to do it, but then I'm going to try to avoid doing it to match with the textbook. I used to make it go like that, right? Because I didn't like drawing a line from the outside going later when I could draw the line from the inside. But whatever. Doesn't matter. As long as it goes back to the while loop or above it, you're golden. You know, get that to go back over here somehow. That's good. And then when the while loop is done, it goes on and it does something else. Right? So as long as the condition is true, and the textbook actually showed it, you know, being just a straight jut from the side. And I'm sure that there's some benefit to doing that for saving space. So I'm going to redraw that a little bit. All right, now I've hit a state where I've got two no's because I deleted I deleted a line and redrew it. All you have to do is double click on that word no and you can rewrite it to say yes. Do try to make sure that there's a yes and a no here. Some people will argue that if it goes one direction, it's always a yes. If it goes another direction, it's a no. Don't do that. The book doesn't show doing that, as far as I know. Yep, they use the word yes and no. We're going to be just like the book. Okay. So that is a while loop. Let's put some descriptions here. These four things are terminators. I'll rearrange everything so it fits on the same page later. Those are the terminators. Down here we have process blocks. Over here we have data blocks. Over here, let's just label it if decision blocks or while. Remember, the book doesn't differentiate between the two. So the decision blocks in action, you have this style. You have the if, just put some text there. That's not emphatic looking enough. Don't know why I have the word yes there twice. I'll clean all this up after class is done. So this is the if style. This is the if else style. Down here we have a while loop. Now just tuck away in the back of your brain the fact that, well, for one thing, you need to memorize all this stuff. But during the exam, since I do let you go and look at PowerPoints and things like that, this is going to be posted as a PDF in our daily notes. So it's just a cheat sheet for our flowchart. So if I ask you what kind of symbol you use to make a decision, pick the diamond, right? If I ask what kind of statement is used for declarations or for math, pick the rectangle. Input, output, you know. So memorize it, but now I guarantee that somebody is going to confuse during an exam or something like that. They're going to use those for math statements, and they're going to use that for input, output. It's just the way some people's brains work, you know. Just like some people are dyslexic or, you know, they just switch it in their brain, and I understand that, but you wouldn't get full credit for it. You got to get the right symbols. Okay, so enough about flowcharting unless there are any questions. We're going to draw a flowchart to match the modules that we wrote on Monday, so we'll get an extra try at it. Didn't mean to launch idle. I'm sure we'll use it though. All right, so a sample payroll report. How did they generate that? They opened a file, they read in some people's information, and then they printed it out, one per person. So open file, while not into file, read a line of data, process it, print it out. Read the next line, while not into file, you know, read, print, next line, while not into file. So just keep looping like that until it's done. Then at the bottom, we print in the report, and then we close the file. Again, that's the housekeeping stuff that sets things up. Opening the file, and then there's some looping, doing some good stuff, and then at the end you just do whatever housekeeping is at the end, even if it's just printing done. You know, that's still housekeeping. Alrighty, now we got a great big flow chart. It's a bit much, but okay, so we have some declarations here. Pretty lousy flowchart because it's blurry when we zoom in. But anyways, okay, start, Terminator. Declarations. You list all of our strings and stuff like that. Now in this language you don't have to declare every variable before you use it. But you do have to declare every variable before it's tested, you know, or its value is used. Right? So if you do x is equal to y plus 3, you better have that y have a value, because otherwise you can't add 3 to it. So nothing wrong with declaring every variable. Some languages require it. Housekeeping. And then if the name is not equal to quit, so I guess we're asking the user for their name. And if their name is not equal to quit, we do some stuff. Ask for some information. We print a line of, of data. And then we go back in. We read another line or ask the user for another line of information. What's your name? If the name is not equal to quit, then we do some more stuff. Now, we talked about a specific kind of value that causes something to stop running. Y'all remember what that value was called? We did it in chapter 1. Like, choose, enter a number or -1 to quit. What's that -1 called? Or enter your name or quit to stop. What's that quit called? Come on, earn brownie points. Somebody's got to remember chapter 1. Sentinel value. Sentinel value. A return statement will exit you out of the loop. I mean out of the module. So it's a good guess. But a sentinel value is the one that kicks you out. Go ahead and burn that in your brain. Sentinel value. It'll probably show up on an exam. So sentinel value is a value of data that is not valid data. Right? Nobody's name is quit. Don't really know about that. But what it does is, instead of being valid data, it indicates the end of the process. So enter a test score or -1 to quit. Hopefully your professor isn't mean enough to give you -1s on your exams. So -1 is not valid data. It is used to terminate the process. It stops the looping. It's important enough to go ahead and put it on our notes again. Sentinel value. Value that ends the loop process. It should not be a valid value, right? Because if you say, what is your name? And then your sentinel value is the word John, that's kind of bad, right? Because somebody's name might really be John. So instead, enter test score or -1 to quit. -1 is hopefully not a valid value, so it is being used as a sentinel value. To end the process, the loop. Once the process encounters the sentinel value, it stops. And that's the example, enter test score, -1 to quit. Or the example in the book is read name. Sentinel values is quit. So if the name was quit, it stops looping. That's example 2. Alrighty, here's something I didn't put on my flowchart cheat sheet, so we're going to have to go back and add it. What is a block with bars? Our flowchart program uses vertical bars. This one uses a, it's a process block. Excuse me, not like that. It's got a special name over here, but it calls a module. What is the name in our flowcharting program? They gave it a strange name. Yeah. Predefined process. If it said module call, I'd be happier. But I didn't write the program. So anyways, let's add that to our cheat sheet. Now, bless you. Okay, just like that. So it's a special kind of process block, but it's invoking something that is defined elsewhere. So it's not math or whatever that's inline in your main program. Instead, it's going to another file to run some code, or it's going to a module to run some code. All right, yay. Well, that was a failed effort. All right, so now we have three kind of process blocks, really. Declarations, math calculations, and module calls. They're all the same shape, except the module call has the bars on it, either along the top, or the sides. So this code shows something called a detail loop. And then the detail loop is a module. I like putting the word DEF in my module name, but you don't got it. You do when you're programming in this language. And then it shows doing some stuff. Input, yeah, so it's in a tilted rectangle, a quadrilateral. It does some stuff. It calculates the deduction. It calculates the net. It does some output. Since that's output, it's also in a quadrilateral, tilted rectangle. It inputs another name, and then it returns. Kind of an odd way. No, I won't say it's an odd way to do it. So when it returns, it jumps back to the end of that so that it can loop. And then there's something called end of job. End of job outputs your last line of your report and returns, so when it comes back here, it stops. There was one more module call here, housekeeping, which came over here. You printed the top of the report, and you inputted a name. The hierarchy chart. All right, until this semester I never taught hierarchy charts. So I'm not going to ask it on an exam myself. But if it's in the Chapter 2 exam / quiz on, on MindTap, answer the questions correctly. The hierarchy chart shows the overall picture about how the modules are related to each other. Tells you which modules exist within a program and which modules call other. Specific modules may be called from several locations within a program. Right? If you write a specialized input function that validates that the user typed in a value between 1 and 10 or whatever, you may call that function in several different places. Notice I'm using the terms module and function interchangeably because that's what our language does. It calls them functions. So that input function, that input module may be called 20 times in your program or 200 times. A specific module may be called from several locations in the program. Planning tool, develop the overall relationship of program modules before you write them. And it's a documentation tool, so you can show it to somebody else. And when you're explaining how your program works, or when your programming team is mapping out how the program is supposed to work or how it does. Okay, so here's a hierarchy chart for the program we just looked like. Remember there was a housekeeping module, there was a detail loop, and then there was an end of job module, and then there was a main program that used all three of those. Alrighty then. And now it starts getting a lot larger. It's got a main program, it's got a housekeeping task, which calls something else, a get order. It's got a detail loop, which calls process order, which calls three other modules. One of these modules calls another module. This is a pretty useful tool, conceptually, to draw things out. And then the detail loop, as well as calling the process order, also called something called get order. And then lastly, the main program called the end of job module. And notice that get order was invoked, from more than one hierarchy. So this doesn't show looping, but it does show which functions are called by other functions. And it also kind of shows that a function is not calling a function above it. You know, check credit, it's not going back up and calling process order. And get order is not calling itself. Now that is actually legal programming under very specialized circumstances called recursion, but we're certainly not going to hit recursion for a long time if we get to it this semester. I hope y'all all will take another programming course as well, like Java or scripting or C++. That's about all I'm ever going to say about hierarchy charts. Read about it, you know. Become more knowledgeable. Become more knowledgeable than your professor. You can, you know, walk around with your chest puffed up big. Use program comments when appropriate. I totally agree. Identifiers should be chosen carefully. Don't just use X, A, and two-letter abbreviations if you can use whole words. Counters are fine for single-letter variable names, you know, for I is equal to 1 to 10, that kind of thing. But pretty much everything else should be a whole word for your variable name. Strive to design clear statements within your modules and programs. Well, what does that mean? You can write code that is hard to read, or you can write code that is easy to read. And I'll give you a little example of that. Now, this is not an extreme example, but you could do this. X is equal to the float version of the input of, what is the temp? That is valid code. Or you could do this. Print, what is the temp? X is equal to input. See, I shouldn't have used X. I should have called it temperature. Why don't we do that? Temperature. And then you would convert it. Temperature is equal to float temperature. Both of these are totally valid. Which one you prefer is up to you. Maybe you think that first line is cleaner. Maybe it's easy for you to spot. Well, I made a typo in it. Kind of thing that, you know, it's easy for y'all to do. Professors do it too. You know, I forgot a closing parentheses there. Why is that? Because for every opening parentheses, you have to have a closing parentheses. For every opening quote, you have to have a closing quote, or else the compiler just gives up. So, which one of these do you think is clearer? You can use either one. This is going along in the direction of doing too much in one line, in my opinion. Here's a more extreme example. A is equal to B that calls C, which calls L. All right. Now, as a mathematical formula, that's a valid formula. But if these were longer function names, like calculate, you know, temperature, you know, convert, you know, and then, you know, modify, something like that, it's getting hard to read. When you could do that as a series of steps, maybe it would be better. Because what's going to happen first is that's going to happen first. I am going to use single letter variable name, sorry, because I just made that thing up off the top. X is equal to modify 10. X is equal to convert L plus 1. Well, I better use that as a Y. And then A is equal to calculate temp X plus Y. Logically, these are the three same things. I myself would rather break this out like this unless this was just like a well-known equation, right? You know, if somebody gives you the compound interest equation and then they say, here, use this compound interest equation. You go, okay, yeah, I'll do it. You cut and paste, you put it in your program. But if you're writing the logic yourself, it's a lot harder to visualize what it's doing if it looks like that than if it looks like that. Now, you may disagree, you know. Some extreme programmers, and I'm not using the term pejoratively, instantly grasp that, understand it. It's okay. I like breaking things down into individual steps. I think that this is easier to read than that. It's up to you. Now, in some languages, you could write an entire program in a single line of code. Now, that's insane, but you could. In Python, you can get a lot closer towards doing that than we do right now by putting multiple statements on a single line, which is certainly not the preferred Python way of doing things, so I'm not going to even show how to do it. Write clear prompts and echo input. What does the echo input mean? It means that after they've typed in something, use what they've typed in back in the output. So clear prompt. Not just a question mark. They don't know what a question mark is. They don't know what they're supposed to type there. It should say something like, how many kilograms? Or convert how many kilograms. Then they type in something, right? And then in your output, you would use that as part of the output. So say they type in 10. Your output could say 10 kilograms is 22.4 pounds. Pretty close. Not exactly. Okay. So this is a clear prompt. You wouldn't just use, K question mark or KG question mark. And in class, when time is of the essence, I tend to make things a little bit more terse. That's a clear prompt. And then echoing your output. Note the input was echoed, repeated, in the output. Now, I didn't ask y'all to do that in your conversion programs, but it is good programming. Why is that? The user may mistype this, especially if it goes to a different screen, right? Because you're filling out your billing information on one page, and then you click order, and then it's going to display your summary. You're not supposed to just have that billing information memorized in your head and trust that it's all done. You actually want to see the order information, right? That's how Amazon does it. It prints the order summary when you're done. That's echoing your input. So that way, if they accidentally type in 100 here, when we get around to the output and it says 220 pounds rather than 22 pounds, they immediately see that there was a mistake there in their stuff, not our stuff. Otherwise, if they typed 100 and they meant to type 10 and it displays 220, and so they ship the customer 220 pounds of gravel or whatever, and the customer gets mad and they blame your program. Your program told me the wrong number of pounds. No, that certainly cuts down them blaming you. It cuts down any misunderstanding. It helps the user understand what the program did. And in cases of making orders, and things like that, patient summaries, order summaries, things like that, it's incredibly important. Your goal is to make the user understand as much as possible. Continue to maintain good programming habits as you develop your programming skills. Yeah, it's a learning process. Program comments. That's the written explanation, beginning with the pound sign. It's not part of the program logic, but it serves as internal documentation. The syntax differs among programming languages. The flowchart. They're calling it an annotation symbol. An annotation symbol holds information that expands upon what is stored within another flowchart symbol. Yeah, whatever. Okay. So the curly braces, I was using annotation symbols. Okay, so examples of declarations. Number of square feet. You can put a comment. Square feet is an estimate provided by the seller of the property. In Python, you wouldn't give it a type, but you would give it a starting value. That's how you declare things in this language. You give them a starting value. Pi equals 3.14159. That's a declaration. Price per foot. And it gives another comment. In our language, the comment's the pound sign. And a lot of them, it's a double slash. I wish that our hero who invented Python had used a double slash, but he instead decided to use it for forward division, which those other languages don't have. And again, you would give it a starting value. One more example. I don't know why he used three, or why this the person who wrote this documentation used all numeric values. Because you could just as easily have a declaration that is a string, you know, file name. Later on, you're going to fill in a file name, the file that will be saved to, like that. So these are all declarations. I would like for you to declare all your variables up at the top, or at least a goodly number of them. But like I said, in Python, you can quite often get away without doing it. You don't have to say x is equal to 0 before later on you do x is equal to y plus z. A lot of languages you do. You have to tell it that x is a number before you can go around and start using it like that. In this language, you don't. So you just have to make judicious mind of what would be a good thing to declare and what not. Or declare everything if you want to, you know, if you want to be thorough. Your declaration should be commented. Not that we do that in every case, especially in here when typing is time is of the essence. Choosing identifiers. This is kind of a rehash of what I said before. Give a variable or constant a good name. Ought to be a noun, right? Radius, pi. How could a variable name be a verb? It can't be. A function is a verb. Calculate pi. That's a function. That's a verb. So give modules an identifier that is a verb. It performs an action. I don't want to use up so much time. We don't have time to draw our flow chart, but name your constants using all uppercase letters separated by underscores. A constant is something that's not supposed to change in the program. The speed of light is a universal constant. Pi, right? Kilogram to pound conversion is equal to 2.204, something like that. Boiling point is 212. That kind of thing. I don't know what the speed of light is. Depends on what your units are. I know that's wrong. Oh, let's Google it. I can't stand for that to be wrong. All right, it's 3e to the 8. That kind of stuff. And then your variables should be lowercase. But you can use mixed case for clarity. Like first name, last name. Or use underscores for clarity. This is considered the more modern style. Underscores are considered more old school. And if you think you can get away with using all lowercase, that's totally fine. I try to do that in here just because if I start throwing in uppercase letters, more typos happen. Why I like underscores rather than mixing the case. Avoid confusing line breaks. Well, our language doesn't support line breaks very much, so I'm going to kind of ignore that. Use temporary values to clarify long statements. I did give an example of that. Up here, when I had this incredibly long formula, like that, This is using temporary values to clarify long statements. So instead of doing that, I did this. Most programming languages are free-form, meaning that you can hit blanks, you can insert tabs, you could remove tabs, things don't have to line up. Python is a modern programming language that is not free-form. You have to tab everything exactly correct. Make sure your meaning is clear. Do not combine multiple statements on one line. What does that mean? Well, some programming languages, and Python actually does support this in a fashion, will let you do this. A is equal to 10, B is equal to A times 20. Print, the answer is B, right? Print, done. You can do all that on one line. Like I said, you can write an entire program, more or less, in one line of code in the languages that support that kind of thing. Don't do that. Just put each one on its own line. This is just another example. Here's a single statement that calculates commission, or you can do that. Besides readability, besides the fact that personally I think that's easier to read, maybe you think this is easier to read, but if you have it calculated like that, you could print these values out to make sure they're working right. You could say, okay, print base property price, print total share price, sales price, print sales commission, and then you can validate that it was working right. If you do it all in one statement, you don't know these intermediate values, so you couldn't really eyeball it to make sure that it's working right. And then later on, you could comment out that print statement when you were sure that your code worked. But if you store your things in intermediate temporary variables, which you use later to calculate your final variable, it's easier to debug. But these are elements of programming style, which means that your program is not wrong if it does that. The prompt is when you display a message and ask the user for a response. What is your name? Other prompts include, a field in a graphical user interface, a window. If you have a form that asks for your name and your age, then that's still a prompt. Echoing input is when you repeat the input back to the user in a subsequent prompt or an output. They typed in their address and then you display a page that shows their address. That way they can go, oh man, I put, the wrong zip code in there. That's echoing output. If I care enough about something to copy and paste it into the notes, that means it's really important. Maintaining good program habits. Plan before you code. Maintain the habit of drawing flowcharts or writing pseudocode. Okay, now I know that after you started doing this, and even in the very beginning, you'd rather just start writing the program. Just drawing a flowchart, that's annoying. But I'm going to make you draw some flowcharts. But eventually we'll get to the point where I don't tell you to draw the flowcharts. If you start writing the program without thinking it through, then you might get stuck. Go back and start planning it out. Do some pseudocode, do some flowcharts. Now, if you're exceptionally gifted, you may just be able to sit down and start coding because you can formulate all this stuff in your head. Not that many of us are going to be that gifted at the beginning. The larger the project is, the more important it is to plan it out. Plan out your modules in advance. Think it through. I'm going to need an input module. I'm going to need a process layout module. I'm going to need a detail loop. I'm going to need a print report module. All of that kind of stuff. Plan it out in your head. Think carefully about your variable names. Design your program statements to be easy to read and use. All right, in a summary. don't think we need to talk about the summary. All right, we have a little bit of time in which to draw a flow chart for our program that we wrote on Monday. Let's see if we can go find that program. I'm going to go to Python. You want to find a program that you wrote recently? You can do launch, idle, and do file, recent files. There's my program. Oh, yeah, that's right. It was a get radius, a print circle, and then I had a test, which I'm going to ignore because that wasn't really part of our circle program or our sphere program. Okay, there we go. Let's see if we can get this flow charted by the end of class. It's always a problem getting this to work because I like having both on the screen, but we don't have two monitors. So go ahead and log into Lucidchart. And if you just wanted to watch and upload a note that said, I'm just going to watch, that's fine. But, you know, this is important stuff. Okay. Let's see if I can bang this over to the side. Bang this one over to the other side. Make room for both. Didn't bang properly. There we go. Alrighty. So a module. You define a module with a terminator just as well as a start-stop. Get radius. That's a module. It does some stuff. Really all it does is input the radius and return it. Now it's actually got 3 lines of code because in Python you do the input, you do the conversion. You have to do all those steps. But in other programming languages you wouldn't necessarily have to do it like that. So I'm just going to use 1 line of code because I should have drawn the flowchart before I did the program. But we did pseudocode it. Okay, so input radius, and then the bottom of a module should have a return statement, another terminator. Return radius. You can see how they match that. These 3 lines were our input, and then we returned. I'm not going to spend the time to tidy things up by making sure they all line up properly. As long as they have arrows, we know what we're doing. All right, now for print circle. What did the print circle do? It calculated the area, calculated the circumference, and then it did some output. And I'm sorry, but I'm going to shorten this. I'm not going to actually show all of that, but what I'm going to do is in this block, I'm going to do print circle again because that's the name of the module. I'm trying to migrate to doing it book style, which is leaving the DEF keyword off. But it has a parameter here that we pass, that accepts the value that we pass in. So I better put that in my module definition. All right. So then we have a math block. Calculate area. That's really lame. I should go ahead and put the formula. I'm saving time. Maybe that's its own, process block later. I mean, its own module later. Calculate circumference. And then print the area and print the circumference. Shows a lot of junk up here that I wish I could get to go away. Print area and circumference. Maybe I ought to put those in 2 blocks. The idea that I'm trying to hone in on here is the module calls more than anything else. The area, let's just go ahead and fill that in. Area is equal to pi times radius to the power of 2. All right. And then circumference is equal to 2 times pi times radius. All right. And then does this return a value? No, so we just put a return statement at the bottom. It doesn't need return radius or anything because we just use those values and we printed them out. We don't pass them back to the main program. So return. All right, so that's our second module. Now this is our main code. Even though I don't have a hashtag start on it, it is our main code. How do we know it's our main code? Because it's the first line of code that's not indented. So our main code follows a start terminator. Can I scroll this one off the page? We all good? You could be putting these things side by side, which is how I would do it if I had more room side to side. I don't hear any typing, but slow me down if you need me to slow down. Of course, I can also print this out and you can do it after class. We have this room available to us for a while. So I'm going to scroll over to the side a little bit. Actually, what I'm going to do is, excuse me for doing this housekeeping, but I'm going to arrange these in columns. So I'm going to draw a rectangle around all of that stuff and then push it back up to the side. I'm going to push all this over to the side of the page. All right, done. Now I'm happier. Now I'm ready to do our main program. Do you have to do your modules on one side and then your main program on the other? No. I actually like using my main code on the left, but since I'm doing it in the order that they were in the code, I put it on the right. So this is the start because it's the main program. And what's the first line of the program? It's a declaration. What kind of shape do we put a declaration in?
Isn't it the bordered square?
Not the bordered square. That's a module call. A declaration goes in the unbordered square, the plain one. So you had the shape right. There we go. Repeat is equal to y. Remember, there should be no dead ends until you hit a terminator, so you always have to hook up the blocks. And then now we have a process block here. Excuse me, a module call. Now we're going to, whoops, I forgot the while statement. While repeat is equal to y, while. The textbook would leave off the word while. I think it makes it so much easier to read that I'm willing to break the rules. Remember that if you want to embed a return, you hit Control Enter. I'm going to expand this to make it easier to read. I think I can remember these 3 lines. I did that wrong. I shouldn't have expanded this. Everything inside of here needs to be off to the side of the while block, right? Because this is the stuff that happens if this condition is true. So just like we tab, we're going to draw an arrow and go off to the right. And what's the first line of our code? Radius is equal to get radius. Well, that's a module call. So the module call is the box, the bars. So radius equals get underscore radius. I wouldn't count off if you just put get underscore radius, but it's nice to show where the results of that call is being stored. All right, under that, what did we have? Let's go look at our code. We had a call to print circle. So since it's not tabbed any more than the rest of it, I'm just going to put it underneath. But print circle is another module call. So I'm going to put it in a block like that. Nope. Print underscore circle. But I have to pass in the radius value as an argument. When you're talking about parentheses, if you have a word inside the parentheses in the header, that's called a parameter. But if you have it in a function call, that's an argument. Sometimes I will confuse those two terms when I'm talking. And then we have to do an input. We have to ask them for the input. Input blocks are, of course, the tilted. Repeat is equal to input, go again, something like that, right? That looks too Pythonese, but really I'm not going to take the time to figure out how I would do it without making it look like Python. Now, if you have an if statement, no line goes back up to it, right? It just branches and then hooks back up. We saw that at the beginning of class. If you have a while, though, that's a loop. So we have to have some kind of line that's going back to it. The line could go on the outside, like the book does it, or the line can go on the inside. I guess I'm just going to follow the book's recommendation and have the line go on the outside. Like that. That's the end of our loop. Let's bring the code back. Compare it. After the loop is done, we have one more statement, a print statement, a print done. So, print done. Nah, let's output done. And then a stop. All right, I know that I went kind of fast. Some of y'all may not have been able to keep up. Ask for a printout of this if you want to continue working on it. I'm going to give you a homework assignment where I give you some pseudocode. It's going to be really generic, and I'm going to ask you to draw a flowchart that matches it. It's going to be kind of like this. Just going to have some module calls. So there we go. That's what our flowchart looks like. We can see what the module calls look like. We can see what the module definitions look like. I'll take roll based on what people upload. So make sure you upload something, even if it's just a note saying you didn't do the flowchart. All right, so what is the homework going to be? Let's make up something that has a couple module calls in it. Now I mentioned a BMI program. Have we actually done a BMI program in this class? Does that sound familiar?
Yes.
Okay, let's I'm going to just write it on the screen. It's easier. So here's what our main program is going to look like. Not smart, but although we are. Pounds equals, or input pounds, good enough. And then pounds is equal convert kilograms. Pounds, like that. So that's a module call. And then input feet, or input inches. And then, that was actually not right. Kilograms is equal to convert to kilograms. Input inches. See, this version of BMI is actually going to use metric units. I'm just doing that so that we have some module calls. And then centimeters is equal to convert centimeters passing in inches. And then BMI equals calculate BMI based on the kilograms and the centimeters, and then output BMI. Pretty easy. That's not too long. We could actually write it like this. Alrighty, so here's a module. Convert kilograms to pounds. Define, convert kilogram from pounds. Kilograms is equal to pounds divided by 2.204. Return kilograms. Remember, in Python, you have to tab the return statement. In pseudocode, you do not. Annoys me. Okay, and then we had one more module. Define, convert centimeters. Centimeters is equal to inches times 2.4. I don't remember what it is. Return centimeters. And again, since this is pseudocode, it has to be unindented. Now, in the programming language that we're using, you have to define your modules before you can call them. So I'm going to cut those statements that I typed and paste them up here. And so the homework is draw a flowchart that implements the logic in the pseudocode below. Make sense? All right. Let's make a Dropbox, and then I'll bring the flowchart code back up on the screen if you need to work on it further. Any questions? Nope. We can hang out for a while if you have questions on homework or whatever. I don't run out of here as soon as class is done, since we have that luxury.